And finally, I want to finish off this lecture by discussing the intensity of the diffraction pattern on a viewing screen due to a single slit or light passing through a single slit. So before we get into the details, let's chat quickly about the general features of a single slit diffraction pattern. So remember, for a single slit diffraction pattern, we're going to have a broad central peak, and that central peak is going to be double the width, double the angular width and actual vertical distance width of the maxima or the secondary maxima that flank either side of it. Also, in between those maxima, we are going to have minima, roughly halfway in between each maxima. And the central maximum for a single slit experiment is way more intense than the secondary maxima that flank either side of it. So you remember that for very small angles, for a double slit experiment, the intensity is roughly equal. Not the case here. So we have a very intense broad central peak and much less intense secondary maxima. And the way that we're going to work out what is the intensity at a point P on a viewing screen is we're going to be going back to phases. So you'll remember that we've looked at phases previously. So now we're going to use them here to determine the intensity on the screen. And what we're going to do is the same way that we determined where the maxima and minima were going to be for a single slit diffraction pattern. We're going to break the slit up into many, many zones, and each zone is going to be the source of radiation, the source of Huygens wavelets. So similarly, with our double slit experiment, we're going to break all our single slit up into many, many zones. And then basically what we want to do is we want to add all the phases at a point P on the screen. And we're going to add all the phases up for the electric component. Remember, the electric component has a much greater magnitude than the magnitude of the magnetic component. So we use the electric component, and we need to add all the phases originating from the slit at that point on the screen. And similarly, as before, the intensity of the light at point P is going to be the square of the amplitude once we've added up all of our phases. So if we're adding up phases from each zone, remember from our analysis of double slits, we need to know the phase relationship between those wavelets that are originating from each of those zones. And remember, as we go further and further down, there's going to be some path length difference between adjacent zones, and when they arrive at point P, they're going to have a different phase. How do we work out what that phase difference is? Well, remember our analysis for determining the phase difference. We would have phi being our phase difference divided by 2 pi being a full wavelength equals the path length difference divided by lambda being the wavelength. So we can do exactly the same thing here. If we break up all of our slits into zones, and those zones have a width of delta y, our path length difference between two adjacent zones is going to be delta y sine theta. Remember the path length difference between two slits that are separated by a distance d sine theta was the path length difference, so similar thing here. Therefore, we can say phi divided by 2 pi equals delta y sine theta divided by lambda. Therefore, let's rearrange this for phi, and we end up with phi equals 2 pi divided by the wavelength, delta y sine theta. So we are assuming, remember, that the waves that are coming in and the light that's coming into this slit, it is coherent. So all of the phases that are going to be added at the point P, they're all going to have the same amplitude. So we're not going to be adding phases of different amplitudes. They're all going to have the same amplitude. Therefore, we're going to have a bunch of phases from all of these different little zones that we're breaking up our single slit into. And the amplitude, the way that we're going to find the amplitude of the resultant electric field at that point P is going to be when we add up all those phases, and we're going to do that via the phasor method. So as an example, let's add up 18 phases, and they're all going to have an amplitude of delta E. So what's going to happen for the central maximum when we add up all of these phases? Remember, the central maximum is when theta equals 0. So when theta equals 0, according to our equation, that would mean that phi is going to equal 0. Therefore, the phase relationship between each of these phases is going to be 0. Therefore, the amplitude of our resultant vector, e theta, at this point is going to be at a maximum. It's going to equal n multiplied by delta E. N here being the number of zones that we've broken our single slit up into. So for example, for here, it's going to be 18. So in this example, the magnitude of our maximum electric field vector, or the E theta, is going to be 18 delta E. But let's have a look at a different value for theta when the value for phi is not going to be 0. So when the value of phi is not 0, what happens is you can see we add up all of our phases and they end up having this cool sort of curved pattern. And the magnitude is just connecting the first phasor to the last phasor. Now the amplitude of this resultant vector, this E theta, it's going to be less than the magnitude of the vector that we found before. So it's less than the maximum. So each phasor is going to have a phase difference that is different from the adjacent one. Remember from our equation before, delta phi equals 2 pi divided by lambda delta y sine theta. Therefore, the total phase difference, similarly to the magnitude that we found before, the total phase difference is going to be n multiplied by delta phi. So we're going to multiply that by the number of zones that we've broken up our single slit into. And that's going to be our total phase difference. So from our equation, we can see that we can simplify it even more. So our single slit, remember, we broke it up into n number of zones of width delta y. Therefore, we can say that n delta y equals a being the total width of our slit. Therefore, let's simplify this equation even more, in that the total phase difference is going to, that's the total phase after we've added up all of our phases, is going to equal 2 pi divided by lambda a sine theta. So now let's look at what are the phases going to look like at the first minimum that we encounter. So you can see that we started off with all of the phases adding up. There was no phase difference between them. And then as we go to different heights on our screen, that the magnitude is going to become less because our phases start curling up. So what ends up happening is, I can't do it with my arm because of anatomy, but essentially what happens is the phases end up curling up and the resultant gets smaller and smaller. So this is what happens when we go further and further out, and we can see the intensity of the diffraction pattern decreasing until they end up curling around completely and making a full circle. And this is where we encounter our first minimum in the diffraction pattern. The amplitude, once all of the phases curl around and make a full circle, the amplitude of the resultant vector is obviously going to be 0. So we have a minimum in the diffraction pattern. And the last phasor is out of phase with the first phasor by, what is it going to be? It's going to be 2 pi. So if the first and last phases have a phase difference of 2 pi, we can actually sub that into the equation we had before. Remember, our total phase difference equals 2 pi divided by lambda a sine theta. So let's sub in for our phi, let's sub in 2 pi. So we end up with 2 pi equals 2 pi divided by lambda a sine theta. And how does this simplify? We end up with lambda equals a sine theta. And you're probably thinking, I've heard that equation before. And yes, you have. It's the one that we derived before, which is the location of the first diffraction minimum for a single slit.